So we have verified our algorithms in model in the loop MIL and validated our generated code in software in the loop SIL. Now comes the exciting part, taking that same controller software and running it on the actual target processor. This is the processor in the loop PiL stage, where simulation meets the real embedded hardware for the very first time. You can think of PiL as the bridge between software validation and hardware integration. In SIL, the controller code was running on a PC, a virtual execution environment. But in PiL, the controller code is now compiled, downloaded, and executed on the real microcontroller or processor that will be used in the actual ECU. The plant, however, still remains simulated. So the setup looks like this. The plant model representing the vehicle system, environment or mechanical dynamics runs on a PC. The controller software runs on the target processor. For example, a Texas Instruments C2000, Infineon Oryx, NXP S32 or Renesas RH850 microcontroller. Communication happens between them typically over serial CAN or Ethernet interfaces so that the plant model sends the simulated sensor data to the processor and the processor sends back actuator commands. This gives engineers a very realistic test setup. The same control software running on the same embedded CPU, but still in a fully controllable simulated world. Now, why do we need PIL? Because this is the first time we can measure how the real processor executes the control code. Every processor has its own quirks, instruction set architecture, clock speed, memory constraints, and timing behavior. Even if your code works perfectly in SIL, it may behave differently on hardware due to timing delays, interrupt latencies, or numeric precision differences. PiL exposes those real world effects early. During PiL, engineers measure how long each control loop takes to execute. This is called execution time profiling. If a control algorithm must run every 1 millisecond but the processor takes 2 milliseconds to finish, you have got a performance issue. Finding that at this stage is critical before integrating into the full ECU or vehicle. Another reason PIL is so valuable is that it verifies compiler and hardware behavior. Compiler may optimize code differently, change variable arrangements in memory, or even alter the floating point precision. By running the actual compiled binary on the target processor, we can detect subtle differences that might not appear in SIL simulations. Let's visualize this with an example. Suppose you are developing a throttle control system for an electric vehicle. The control software reads a pedal input, computes a torque demand, and sends output commands to the motor controller. In PIL testing, the pedal position, motor speed, and torque sensors are simulated on your PC as the part of the plant model. This simulated data is sent to your microcontroller via a communication link. The controller code executes its logic on the real chip and sends actuator signals back to the PC simulation, which updates the virtual plant model accordingly. If everything behaves as expected, throttle response, torque output, and timing all match the simulation, then your control software is validated at the processor level. Another powerful aspect of PIL is profiling and optimization. Engineers use this stage to optimize CPU load, reduce execution time, and check memory footprint. They can evaluate how much RAM and flash memory are consumed, how many CPU cycles are needed per control loop, and whether the code meets real time constraints. By doing this before full hardware integration, they ensure that the ECU will have enough processing power to handle all control tasks safely and efficiently. Let's also talk about communication latency, an important factor in real embedded systems. In SIL, data transfer between plant and controller is instantaneous, but in PIL, real communication interfaces are used UART, CAN, SPI, or Ethernet. This introduces real world timing delays. PIL testing helps measure and compensate for those delays to maintain stability and responsiveness of control loops. Now, what kind of issues can PiL testing uncover? You'd be surprised how often real processors reveal hidden bugs that software simulations miss. For example, integer overflow in fixed point arithmetic, stack overflows or memory leaks, compiler optimization differences affecting control outputs, timing jitter caused by interrupt service routines, real CPU load exceeding expected limits, floating time rounding variations. PiL exposes all this without the cost and complexity of full hardware integration. Here is another benefit: fault injection and diagnostic testing. Engineers can inject simulated faults like sensor noise or signal dropouts and observe how the real processor software handles them. Does it detect the fault? Does it switch to backup logic? Does it log diagnostic codes correctly? These behaviors are critical for automotive functional safety and ISO 26262 compliance. Speaking of ISO 26262, PiL testing is a key step in safety critical software development. It provides concrete evidence that the software behaves as intended when compiled and executed on the target hardware platform. Many OEMs and Tier 1 suppliers use PiL results as the part of their safety documentation and verification reports. Let's list 10 key things typically verified in PiL testing. The checklist every embedded developer lives by: processor execution timing, verifying loop times, task scheduling, and CPU load under realistic conditions. Numerical precision, ensuring results match SIL within expectable tolerances, accounting for floating or fixed point differences. Compiler optimization behavior, checking that different compiler settings don't change control outcomes. Memory usage and stack behavior, verifying static and dynamic memory allocations, preventing overflows. Interrupt latency, measuring how quickly the processor responds to simulated events. Code performance under load, simulating heavy data throughput or concurrent tasks to test stability. Task prioritization and real-time response, ensuring high priority control tasks always execute on time. Communication timing, validating delays over UART, CAN, or Ethernet interfaces between plant and processor. Error and exception handling, ensuring graceful recovery from unexpected processor or data faults. Power consumption profiling, measuring processor energy usage for low power embedded applications. Each of these gives developers confidence that the embedded code isn't just correct, it's efficient, stable, and hardware ready. Now, an important note: in some setups, PiL and Hill are closely related. The main difference is that in PiL, only the processor is real, not the entire ECU or sensors. The rest, plant, environment, sensors, actuators, remain simulated. Hill, which we will explore next, takes this a step further by connecting everything to real hardware interfaces and physical I/O. Another reason PiL is so powerful is that it allows developers to do closed loop debugging. Because the processor communicates continuously with the simulation, you can step through code, set breakpoints, or inspect variables in real time while the system runs. This visibility makes it far easier to understand timing behavior and fix subtle bugs that could be hard to trace in a complete hardware setup. PiL environments can also be fully automated. Using tools like MATLAB Simulink Real-Time, dSPACE Box, or ETA's Inca with embedded target interfaces, engineers can script PiL tests, collect logs, and compare them automatically with the SIL and MIL reference results. If discrepancies appear, they can immediately isolate whether the issue came from the processor, the compiler, or the algorithm itself. Here is a quick example from the automotive world. Testing a motor control unit (MCU) for an electric power steering system. The control algorithm implemented in C runs on a TI C2000 microcontroller. The virtual steering system, vehicle dynamics, steering column, road load, and driver input is simulated on the PC. The PC sends sensor data like torque and steering angle to the microcontroller via CAN. The microcontroller executes its control loop and sends back actuator current commands. Engineers monitor how closely the motor torque follows driver input, how quickly the control loop responds, and whether timing deadlines are met. This PiL test confirms both functional correctness and timing performance. If the code runs reliably on the real processor under these conditions, it's ready for integration into a full ECU prototype. Another growing application of PiL is in multi-core and AUTOSAR systems. Many modern ECUs use multiple cores or even multiple processors running in parallel. PiL helps analyze how these processors communicate, synchronize tasks, and share data all before physical vehicle tests. Finally, one of the biggest advantages of PiL is cost saving and safety. Running the software on the target processor while keeping the environment virtual means no risk of damaging hardware or vehicles. You can test dangerous scenarios, sensor failures, extreme loads, or corner cases completely safely without putting real components at risk. To summarize, processor in the loop testing ensures that your control software not only works in theory but also performs as expected on real embedded silicon. It validates execution timing, memory usage, and computational precision, providing a crucial confidence layer before full hardware deployment. So, in short, MIL verifies your algorithms, SIL validates your software, and PIL proves your processor performance. Once you have passed the PIL stage, your control code is ready to face the real world. The next step being hardware in the loop, where your controller hardware interacts with real signals, sensors, and actuators in a physical test setup.